If you guys got any questions right now, I mean, we can
Yeah,
kind of
go
go
for it.
through them while we wait for everybody to show up, and then, obviously that will maybe minimize some of the questions as we go. And sometimes it's always good to hear, once you get through the presentation, as questions uh, come up then too. So you have other questions you can ask.
Anybody got questions? Go for it.
Well, if everyone else can be quiet, Bob, I've got one for you. What is the difference between quick and thick and speed set?
So I always call speed set quick and thin. So really the only difference is well, there's a couple of differences. So viscosity is kind of one of the major differences. The quick and thick doesn't run. Um, I like to use that. So I was making a table and I ended up cutting the joint on the wrong side of the line. And so my joint was very, very loose. And so if I use Titebond 3, which is my usual go-to glue, it would have just run right out of the joint. So I switched to Quick and Thick in that particular instance. It stays where it is. It's relatively high solid, so it will fill gaps a lot better than, say, the Titebond 3, which is 50% solids. And so I used the Quick and Thick for that. So that's a good one to have kind of in your holster to use for maybe joints that are a little loose. It fills gaps a little bit better. The Quick and Thick also it's a it's a lot easier to handle because it just doesn't, how do you say, drip. So if you got squeeze out, it's going to stay wherever the squeeze out is. Now the speed set is a little bit is a bit thinner. And so it's going to run kind of like Titebond 3. I don't know if you've used Titebond 3. It tends to be a little runny and drips quite a bit. Now, one of the advantages of the speed set is it's a very hard glue. It also has a UV dye added to it so that you can, if you're going to stain something, you can use a black light and it'll show up it'll fluoresce back at you, even in regular light. I mean, it's going to shine bright white back at you, so you know where to sand the glue off of the wood before you stain. Because there's always a pain in the butt when you go to stain something and then you see where all the glue has kind of soaked into the wood, and you've got, excuse me, you've got this bicoloration. You got to kind of sand that off again and then start over with your staining. So that's one of the benefits of the speed set. The quick and thick is a little more flexible than the speed set. And that's because the quick and thick was our old molding and trim glue, right? And so the molding and trim glue had to, let's say I've got a cabinet and I want to put a molding piece on. With the quick and thick, I could just put the glue on the gluing surface of the molding, stick it to the side of the cabinet, rub it till I feel it grab, and then kind of hold it there for 30 seconds, then I can let go. You don't really need pin nails in that particular case with that glue. So you're not having to fix pin nail holes, or if you want to put a few in, you can, but you don't have to put as many in. The glue is flexible enough to allow that cabinet to expand and contract with moisture, because that trim piece is not going to move at all because it's longitudinal direction versus the other direction. So it allows for some wood movement capability. So
Which one would grab the quickest?
they both grab very quick. They both grab very quick. So if you're doing a rub joint, let's say if you're doing
Doing
a
like,
ring with a ring
yeah,
with a lot of pieces, you could just put a drop of the speed set or the quick and thick onto one side, rub them together until you feel them catch, get them into place. Then you can just wait 30 seconds, then you get onto your next piece. And you really don't need to clamp those. I know a lot of the segmenters like to use, clamps on those or rubber bands and all that, but you don't need that. The quick and thick does a very good rub joint. And if and a lot of people usually say, well, what I'll say is just give it a try and, play with it. And you'll find that you don't need to clamp your rings at all.
What kind of shelf life would that have?
So Quick and Thick and the Speed Set have an official 2-year shelf life. But really, really only my lawyers care about shelf life. What you guys really care about is the usable life of the product, right?
Yeah.
So how long is it going to remain usable? And usually for non-reactive adhesives, basically those that are not water resistant, usually get, if you store it indoors in good conditions, usually get 10 years of use out. Um, the the water can evaporate through the bottle a little bit. So you can always add a little bit of water, up to 5%. But you got to be real careful because a little bit of water goes a long way to risk dropping that viscosity down. So it'll get pretty runny on you pretty quick. So
So why does it react glue so well, so quickly, and yet it's in a bottle all this time and not going hard?
So the issue is that, and we'll go through that in the presentation, but everybody's rubbed wood glue between their fingers, right?
Yep.
Real slippery. Well, all of a sudden it's going to get to its what I call the putty point. And that's the same thing on a rub joint. When you start rubbing it, it's pretty slippery, and then all of a sudden it starts to catch. Well, when it starts to catch, it's kind of like filling a jar full of marbles, right? All the marbles are touching. If you look under a microscope, wood glues are just microscopic balls of plastic that float in water. And
I don't know.
I mean, that's all they are. And I'll have a picture of that for you guys to look at. But at some point in time, the balls get closer and closer and closer together, so they start to touch. Once they start to touch, they can't move any longer, and so they get relatively rigid, and that's when the glue sets. Now, Speed Set and Quick and Thick are 60% solids. The theoretical amount of spheres that are all the same size would be as if it got to 67% solids, it would lock up because the balls are now touching and the water will fill the space between them, which is about 33%. So the Quick and Thick and the Speed Set only have 7% water to play with, whereas like Titebond 2, Titebond 3, Titebond Original, they're about 50% solids. So you've got 17 to 20% water to play with. You got a lot more water that allows the glue to stay open and workable for a while. Now with Titebond 2 and Original, we can play with that. We add a little bit of borax, and the borax causes it to coagulate at how would you say, a lower level, right? And so they're designed as production adhesives. Whereas Titebond 3 was really designed as kind of a do-it-yourselfer, long working time. It doesn't have the borax in it, so it doesn't have that quick grab. Does that make sense?
Yep.
And we'll go through a bit of that. Once we go through the whole presentation, you'll get a pretty good idea at that point.
Okay, thanks, Bob.
Okay, well, it looks like we're rolling right up onto the hour. So having said that, I'm gonna mute all just so that everybody gets muted at the same time. And like I said before, if you have a question, don't feel bad. Bob will give us a break to answer the question. Hit your space bar to unmute, and then when you're done with your question, please mute yourself again. And that'll get rid of any background inadvertent things. So here you go. I'm going to mute everybody, and I'll unmute you, Bob, and we'll let
Okay.
you carry the ball.
All right. Let me get to share, and everybody can see the screen. So just a little bit about myself. I'm the technical service manager for the Titebond brand. So that includes not only wood glues, we do sell construction adhesives, we sell caulks and sealants, we sell flooring adhesives, drywall adhesives, and all kinds of other adhesives too. But tonight we're going to focus on wood gluing. And let me see if I can get this actually to work. There we go. So wood is really the original composite, right? It's light, it's strong, easily worked, retains its stiffness long periods of time. It's low cost, sustainable, and really the reason we really love to work with wood is, I mean, it is just a beautiful substrate to work with, right? I mean, it comes in all different grades, all different oak, maple, the tiger wood, just wonderful, wonderful substrate to work with. But because it's a natural product, there are some properties of wood that will affect its gluing capabilities, right? So kind of one of the easier ones to kind of talk about is wood density. So normally I'll get calls all the time on the phone, and the calls will start with, I need your strongest wood glue. And how I put it is, it's going to depend on the wood, right? So if you're gluing, so the guy who called and I asked him, I said, so what you doing with it? He goes, well, I'm making model airplanes. Well, if you know anything about model airplanes, most of the time they're using balsa wood, right? And balsa wood is going to break somewhere around 40 to 60 psi, right? So I could sell you a 4,000, 4,200 psi wood glue, but that's still going to break the joint at the 40 to 60 psi that the wood is going to break. So when we look at from the gluing side, we look at what's called the chain of adhesion, and this is going to be important as we go through talking about gluing. So I have substrate A, and then I have the interface between substrate A and the glue, and that interface is where the glue actually bonds. And we'll talk about, how the glue bonds to the surface. Then we have the strength of the glue itself. Then we have the interface to substrate 2, and then we have the strength of substrate 2. So the weakest link in that chain is going to be the determinant of how strong that bond is going to be, right? So if I'm gluing paper to high strength steel, right, that joint is going to break at what paper breaks at, which is going to be about 40 psi, right? So again, we want to kind of keep it in perspective. When we go through this presentation, we'll be talking a little bit about joinery and stuff like that, just to kind of go through what is the glue doing, what is your joinery doing, and how can you best incorporate those together. So the other thing we want to talk about is moisture content of the wood. Now, when you cut a tree down initially, it could be up to 200% water. So basically they have to dry it. And as the tree dries out, it gets to the point where it starts to shrink, and that's going to start at about 30% moisture content. So everything above 30% typically tends to be what's called free moisture, and then everything under 30% is bound moisture. And that bound moisture is bound to the cellulose itself in the wood. And as the cellulose dries out, the wood starts to shrink, right? So when I'm talking about all of during this presentation, all of our testing is done at 8% moisture content. We also test at 70 degrees Fahrenheit, which is lab temperature, I think, 23 degrees centigrade. And then we also look at 50% relative humidity. So everything that I'm going to tell you is going to be in this, under these conditions. Now, obviously in winter, up in Canada, when it's minus 40 degrees out, there's not a lot of moisture in that air. You bring that air into the house, heat it up, your relative humidity can get very, very low. And in that case, your wood is probably going to be somewhere around 2 to 4% in those cases if you're not humidifying your house. And so therefore the glues are going to dry a lot faster. Now, if your wood by chance gets above 17% moisture content, water-based wood glues will not dry at all. And because there's enough moisture in the wood that the wood doesn't really need to soak it out of the glue line. And so in that case, you'd have to wait for your wood to dry out before the glue actually dries out. So we just want to be cognizant of that and know that whenever I'm talking about, how long it needs to be in the clamps, open time, working time, all of that is going to be at 8% moisture content and 50% relative humidity. And that can change, I would assume, seasonally where you guys are located. In the summer, I would assume it gets a little humid, right? And so therefore your wood moisture content may be above, up around 10%. So we just want to be cognizant of what can go on. And I'll kind of fill in on some cases where that really becomes an issue. Questions at this point? Okay, I'm going to move on. The next thing we want to talk about is dimensional changes associated with these changes in moisture. So a tree itself the wood from a tree doesn't consistently shrink the same in every direction. So when we look at a tree from the roots all the way to the tip of the tree, the wood that's cut in that direction we call longitudinal, and the changes in moisture are very little. I mean, to the point where we can really forget it. It doesn't shrink and swell with moisture very much in that direction at all. When we look from the middle of the tree to the bark, that's called the radial dimension. That radial dimension will shrink by X. And when I say X, that X is based upon the species of wood that you're looking at. So each species is going to have a different moisture content, contraction, and expansion ratio. When we look at, say, a poplar tree that's grown up north versus one that's grown down south, they're also going to have a different expansion and contraction ratio. It has to do with the cell structure of the wood. The other dimension that we look at is what's called the tangential direction, and that is actually as you follow the bark all the way around the tree. And that tends to be 2x, or twice the amount that it shrinks and swells in the radial direction. And so what happens there is, and you can see the log as you cut wood from each parts of those logs, they have a tendency to want to warp, twist, and shrink in different directions, mostly. So we want to be cognizant of that. Now, because of those moisture changes, I'm going to go to the next slide. Everybody can see this? Just want to make sure because this is our first.
Yep.
Okay. So let's say I glue 3 pieces of wood together, right? That middle piece is at 10% moisture content. The 2 outer sides are 6%. Or this could be that I am gluing walnut in the middle and then maybe pine on the outsides, right? Don't know why I would do that, but again, different moisture, how would you say, shrinkage and swell ratios, right? So eventually it's all going to equilibrate, right? It's going to get to the, how I would call the use moisture content. And so if that was the case, if I was using boards that were of different moisture content, and this you see mostly for tabletops, you know, when you do a tabletop, you do that final sand, everything's flat and smooth, you put your finish on, it's like a mirror, right? And then over time I look at it and now I've got one of the boards, it seems to be a little thinner than the other boards. This is due to the moisture content of the board, and the wood will shrink. So even like what I show here is plain sawn boards, right? And so plain sawn boards are going to have that cathedraling to them. And in that particular case, when they shrink, they tend to want to warp. The outside of the rings tend to, can you see my pointer move?
Yep. Yep.
Okay. So it will tend to shrink more on the outside of that ring than on the inside of that ring, right? Because you have more tangential wood here than you have here. And so this will tend to warp in this direction, right? This board will warp in this direction. And so you'll end up with kind of, how do you say, a wavy look to the board. If it is quarter sawn or rift sawn, then the grain is going to be up and down, right? And in that case, then in the tangential direction is going to be basically in thickness, right? And so thickness is going to be affected by boards in this direction. Now, if you're a segmented wood turner, turning your, how do you say, your grain in different directions on that ring will then cause that ring to be dimensionally changed differently. Does that make sense? So you just want to note what direction your grain is going into. So you want your rings to expand and contract together, kind of in tandem. And so you don't get one ring wanting to expand and contract more than the other ring. Okay? Questions at this point in time?
Yeah. You have a slide that shows that?
That shows the what?
Different directions for the wood grain.
I do, but I have a separate presentation that's called Wood University. So I can give that to you guys at a later time, but it kind of goes more into depth about specific wood, how wood grows and things like that. So we're not going to kind of go through that. This is more of the wood gluing instead of the wood technology, so to speak. But I just wanted to hint at it in the fact that you need to have a little bit of knowledge about this movement of wood so that when you're putting these, how do you say, these pieces together, that you're not getting this shrinking and swelling in different directions so that it kind of warps the product a little bit, right? And I know there's a lot of people who do green wood turning, and the green wood turners know this already, right? Because you can turn something, it looks great, it looks round, and then after a couple weeks or a couple months, it is no longer round. It can take some very funky shapes, and that's the whole idea about green turning, right? So we're going to move into the next one. This one has to do, and you segmented turners are going to get a little, the light's going to kind of go off. So let's say I glue a board up, right? So as soon as I glue it up, the wood around the glue line is going to swell due to moisture increase, right? If you're using a water-based wood glue, the wood is going to swell. If I then take that and turn that right away, or if I plane the boards off before it has a chance to the swelling to go down, what's going to happen is I am going to get a flat surface here, but around the glue lines, as the wood dries out, the wood will shrink. The thing is, the water-based wood glues, they are plastic and they're not wood. So they're not a natural product. And so they are not going to shrink and swell with the wood. So what's going to happen is those glue lines are going to be at the same height as the board was when you turned it or sanded it or planed it. And now, because there's a dip in there, your finger will actually feel this ridge. And we'll get calls and people will call me and say, your glue is extruding from the glue line. And my statement is to them, well, how do you get hard plastic? Because everybody here is scraped dried wood glue, right? I mean, it's a very hard plastic to the point where it can be very difficult to actually remove from the wood without removing the wood with it. And so how would you get a hard plastic to extrude from a glue line if you don't have a lot of pressure on that wood, right? And the pressure would have to be almost to the point where you're crushing the wood itself, right? And if whoever figures out how to do that, by the way, if you can get glue to extrude from a glue line without any pressure being put on it, give me a call. You've violated the laws of physics and we're going to be filthy rich. So again, we want to be cognizant of, we've got to allow the wood to shrink back before we do our final sand. The other thing that can happen is just normally, let's say it's summer, the wood content is 10%, and then in the winter it dries out. Now that wood is 6%. So at that point in time, the wood's going to shrink, the glue lines are not, and you're going to feel the glue line. And I know, and I've done some segmented turning, and you do that final sand, right? And it's baby smooth. I mean, there's nothing like that feel of the final sand on a turned item, right? I mean, it's just, with 300, 320 grit, maybe even higher in some cases. I've seen some people go up to 1,000 and get that real polished look on the wood. But the problem is once I get that off and then the moisture changes in the wood itself, now I can feel every glue line. Well, this is what's occurring. So to keep your glue lines from happening like that, what you have to do is you have to dry it way out and then do your final sand. Then as the wood expands, it forms a divot, but your finger can't feel a divot like it can feel a ridge. A finger can feel a ridge of 2/1000ths of an inch, whereas for a divot, I think the divot actually has to be like 10 to 15/1000ths of an inch. So again, you want to be cognizant of if you're feeling differences in there. The other thing on a segmented turning is if you've changed your grain in different directions, right? Some of the boards will shrink more in one direction than the other direction. And so then you'll get a different feel for it also as the moisture changes. Questions at this point?
When you look at the different directions that you're showing in your slide, one side the grain is going up, in the middle they're going down, and then again on the up. Is that, I've heard some people say that that doesn't make a difference.
So what'll happen is that wood will warp in different directions, right? So I'm going to get this wood warping this way. So it's the warping of a plain sawn board is always going to be opposite of what the grain rings are, right? And then this one is going to go this way. So what'll end up is happening is I'll have a board that goes up here, down here, and up there, right? And so it's going to be wavy feeling. Now, and this is more important for tabletops. Most of the tabletop guys will tell you do not, how do you say, change the grain direction from board to board. Put it all in the same direction because it's easier to deal with a large warp in one direction than it is small warps in multiple directions, right? So if you want your wood all to go warp in the same direction, you got to kind of look at, have I got it all in the radial direction or is some of this in the tangential direction? Note that the tangential is going to shrink more than the radial direction. And so this is, that's why when you have changes in moisture, that vase or whatever that you have made, it's going to feel different. It just is. And that's the nature of wood. Now, if you use hide glue, okay, hide glue is a natural product and it actually does expand and contract with moisture also. So hide glue will not be as noticeable in terms of, the sunken glue lines or the proud glue lines of here. But then you run into the issues with hide glue, which is it's not resistant to humidity. And so therefore on a humid day, it could fall apart on you. Hide glue is known for being able to take it apart with a little bit of steam, right? A little bit of humidity and the joints soften up so you can take them apart and repair them. That's why a lot of violins are done with hide glue because it takes you a long, did I mention a long time to do a violin? And if you broke a piece of wood to have to redo that piece with the same acoustical properties, it is amazingly difficult to do.
So I have a question.
Yeah.
So I get everything, excuse me, I get everything you're saying about the changes in moisture content, but once you put a finish on that wood and seal it, supposedly sealing both sides, even of an underside of a cabinet, you shouldn't have nearly that many problems, correct?
Well, so it will slow the process of moisture movement through the wood because it's basically, let's say I got a bottle of glue, right? And polyethylene, which is what the bottles are made of, have a very low moisture vapor transmission rate. But the bottles will eventually dry out over time as moisture moves through that plastic. So moisture will move through that plastic. And depending on the type of plastic or finish that it is, some of them have very high moisture vapor transmission rates, where, the amount of moisture that can move through there. But they will differ, right? So it just depends on what the polymer is made from that is the binder for that finish. But it does slow it down, but it will not fix it. I've seen tables on this sunken glue joint, and this was a table that was made on the coast of California, and they sold it to, and this was a $25,000 table, and this guy, let's put it this way, he would have made a sailor blush with the words that was coming out of his mouth, and so what had happened is he sold it to a guy in Phoenix, Arizona, and the table dried out and the finish actually popped up off the table where the glue lines became proud of the wood surface. And so he had white stripes along all of the glue lines. And of course, the call comes in is, the glue sucks, it's all the glue's fault, right? But in this particular case, it wasn't, no matter what he used, whether it was our glue or anybody else's glue, because he did not get the wood down to the moisture that it was going to be used at. The glue lines were going to be proud no matter what, right? Even if he waited, the time, and normally I get the question, well, how long do I have to wait to keep the step, the sunken glue joints from occurring? Well, if you call me and ask me, my assumption is you have a lawyer on the other line with you. And so you're going to be holding me to this, and I'm going to tell you 3 weeks. And most people go, 3 weeks, you're full of bologna sauce. I can't wait 3 weeks. I said, well, so how long can you wait? So really what it is if you can wait 24 hours, it's going to be a 50-50 shot, whether those step joints or sunken glue joints are going to occur. If you can wait 3 days, usually you get rid of about 75 to 80% of the problem. If you can wait a week, you can get rid of 90 to 95%. But if you're asking me for 100%, I've never seen anything occur of sunken glue joints after 3 weeks. And so that becomes the issue, right? How long do you want to wait versus, how important is this problem? But note that the problem is going to occur if the moisture changes in the wood. It's just going to happen. So the only way to get rid of the feel of that is to get the product down to its lowest moisture content and then do your final sand and then just let the moisture go, because your fingers aren't going to feel that crevice, right? The depression, a finger cannot feel the depression, but it will feel the ridge, the thinnest of ridges. And everybody knows that. You use your finger as kind of a measurement on how well you got your wood together, right? So, other questions?
It all comes out to the amount of humidity that you have in your house, or non-depending on where you are in the country.
Right. And so it's going to vary depending on where you are in the country. So if you're making a product for somebody in a different area of the country, you're going to need to know, what the moisture content is going to be in his house. Or one of the things that I tell people is, then you've got to tell him that the problem is going to occur. If he doesn't keep his house humidified, and the guy who did the table could have just told him, listen, you got to keep your house at this moisture content or humidity. If you don't, then, the table will pop the finish and you'll get white stripes on your table. Or if he would have told the person that, then he would have been the goat and not the goat, right? You get the greatest of all time versus the meh, right? And that becomes the issue. The more you know about this and you tell your clients, especially if you're selling very expensive stuff, if you can come off as being an expert that, hey, this is what's going to happen if you do this, and it actually happens, you don't lose the value. You actually increase your value, even though the problem was still there.
What happens if you, sorry, what happens
No worries.
if you blew up some vase that is 8-10% humidity in your shop, and then you put it in somebody else's house that has a 25% humidity in the house? There will be a big difference in the wood that how it works with their glue.
Yeah, I mean, if it goes to a different moisture content, the wood is not going to be the same, the same dimensions. And that's just the nature of wood. Whether you want it to or not, wood is going to take a shape that it wants to be, not the shape you want it to be, right?
Okay.
You can coax it into a shape, but as moisture changes go by, it's going to do what it wants to do, and not what you necessarily want it to do. Now, knowing grain direction, knowing this, knowing that, squirrely grain tends to warp things in squirrely directions too, right? And so again, the more you know about this, the more you catch, then it makes it easier, A, to explain any things that goes on. And hopefully you're not going to blame the glue in that case. And that's the reason for these presentations.
I have a related question. If you're talking about a turned bowl, the amount of warpage is going to be so much different than, say, a table, isn't it?
So let's say I've got a bowl, right? If I've made a bowl, I'm going to have the radial direction, and I'm also going to have the tangential direction, especially if I've got the middle of the tree in there somewhere, right? Or if I've got wood from just one side, right? Then that grain is going to warp differently depending on which direction it is. And so I may make it round at some point in time, but as the moisture changes, it's now going to get oval, right? It's going to shrink more in that tangential direction than it's going to in the radial direction. So it will not be round any longer if the moisture changes from where you turned it.
I
Or your
understand that. I mean, with a segmented bowl, the pieces are so small, the amount of change is going to be minimal.
It depends on if they are all in the same direction, right? So if you've changed them back and forth, then you're correct. They'll cancel each other out. But if the grain is all in the same direction, you'll still just as if it was from a how do you say, single piece of wood, right? So again, you're just going to have to look at that grain direction in a new light, right? And then note that this piece, that even though it's small, is going to change in this direction. This piece is small, is going to change in this direction. Do they cancel each other out or do they add? And that I won't be able to tell you. You'll just have to look and see. But now that you know that the tangential direction is twice than the radial direction, that may help you kind of understand that a little more. And then if something does occur, you go, oh, well, that's what it was. Make sense?
Thank you.
Okay. The next thing we want to look at is the other stuff that's in wood, right? Pitch, oiliness, contaminants, tannic acids. So this is the stuff that the tree makes to protect itself, right? So a tree growing in the woods, termites move into the area. A tree can't just go, well, there goes the neighborhood and move away, right? So it's got to stay there and it's got to fight. It's got to fight these insects. It's got to fight the bacteria. It's got to fight the fungi. And to do that, the tree manufactures chemicals. And these chemicals, the oils in these tropicals are used when termites eat it, the oil plugs up their digestive system so they can't digest the wood and the colony dies. And so the issue is, and I want everybody to unmute your buttons and say whether they believe wood glues work through the pores of the wood or through a chemical means.
Chemical.
Pores.
All right. So the person who said pores, I'm going to challenge you on that. If pores were the major contributor to the strength of a wood joint, what would be your strongest joint? Would it not be end grain to end grain?
End grain to end grain, yeah, right.
Right? But it's not.
Okay, I see your point. Yeah.
Yeah, end grain to end grain tends to be the weakest, right? And so I'm going to go through a little bit of chemistry. Sorry, I'm a chemist. But the glue actually bonds to the cellulose of the wood. And let me show you how. So trees produce glucose, which is a sugar. And then they polymerize it together. Basically, they take this sugar molecule, attach it to another sugar molecule, which then attaches to another sugar molecule, right? So wood pulp has between 300 and 1,700 of these units put together. Cotton, because it is a tougher, right? So I can make clothes out of cotton, and those fibers can bend back and forth and not break, right? Unlike paper, when you bend it back and forth, tends to break. And so the larger the molecular weight of the chain, the tougher the polymer becomes. But that's kind of getting off track. How wood glues work are through these groups here. They're called the hydroxyl group. Oxygens love electrons and tends to pull the electron towards it. Hydrogens, on the other hand, tend to not really care about the electrons, and so they'll give it up. What happens is the oxygen tends to get a net negative charge. The hydrogens get a net positive charge. And so these are like little atomic neodymium magnets, right? So let's kind of take that neodymium magnet kind of idea. If I take a neodymium magnet and put it on my fridge, right, and then pull it off, I can pull it off pretty easily, right? Now let's take just one molecule of cellulose from wood, which has 300. So let's just go say 500. I am going to have 500 times 3. So I'm going to have 1,500 neodymium magnets. So let's go ahead and place 1,500 neodymium magnets on my refrigerator door and try to pull them all off at the same time. What happens? I will pull the refrigerator door off. And this is how wood glues work. So wood glues have what are called, so it's got polyvinyl acetate. Polyvinyl acetate actually doesn't stick to the wood. It doesn't have very many hydroxyl groups, or what I call polar bonds, to actually bond to the cellulose. What we do to stabilize the polyvinyl acetate plastic, which is heavier than water, to keep it from just sinking all the way to the bottom, we also add polyvinyl alcohol and polymerize it with it. Polyvinyl alcohol has tons of these hydroxyl groups. Well, what happens when you get them together, right? Well, a hydroxyl group, which has got a net positive charge here, will want to cozy up to the oxygen on another chain. And so what ends up happening is the closer you get these two together, the stronger the bond, right? So let's go back to the neodymium magnet. So that neodymium magnet, if it gets very close to the metal itself, right? If it's just bare steel, it can be really hard to pull off. If I take a couple pieces of paper and put them between there, now it becomes easier and easier to pull off. And that has to do with how close those charges get together, and that electrostatic charge causes them to stick together very well. And that's going to be important as we go along. Now, I got a question at one of these presentations, and the guy who was a definitive, works through the pores of the wood, wasn't believing me. He said, well, the pores of the wood have to add some strength to the bond. And I was like, well, I don't know. So I went back to the lab and I was like, how am I going to test this? Right? Because all of our wood glues have the hydroxyl groups on them. So the guy who developed Titebond 2, he's retired. He comes in because he gets bored in retirement. So he comes in usually about once or twice a week. And his name's Chuck. And Chuck was walking down the hall. I said, hey, Chuck, come here. I said, Chuck, can you make me Titebond 2 without the polyvinyl alcohol? And he kind of stared off into the air, and you could almost hear the gears cranking in his brain, and he just walks off like, Chuck, did you hear me? And so it was actually about 2 years later, he comes into my office and he puts this bottle on my desk. This is 2 years later. I go, hey, Chuck, how you doing? He just dumped the bottle on my desk and he was walking out. I was like, Chuck, what is that? He goes, oh, that's what you wanted. I said, well, what did I want? He goes, that's Titebond 2 without any polyvinyl alcohol. I said, great. So we did some testing, right? So we glued some chunks of wood together, and then we break them in shear, right? So we put them in the vise, in the testing machine, and it pulls them apart in a shearing action, right? So when we tested that, the Titebond 2 without the polyvinyl alcohol broke at 800 psi. When we broke the Titebond 2 with the polyvinyl alcohol, it broke at 4,000 psi. So we do know that the maximum amount of pore bonding that the PVA is doing is about 20%. But the issue is, and I should have thought about this before I asked Chuck to do something, was, well, Titebond 2 has a chemical in there that allows the glue to be water resistant. That chemical also chemically reacts with the hydroxyl groups. And it's not just an electrostatic bond, it is an actual chemical bond right to the hydroxyl group. And so that's going to contribute to that 20%. So in my estimation, just noting the amount of, it's called N-methylolacrylamide for any chemists out there, that's in the Titebond 2, my estimate with the amount that's in there was that really the pore bonding is going to be between 5, maybe 10%. So somewhere in there. So the pore bonding is very, very insignificant as compared to the hydroxyl bonding. And once we understand that, it makes a lot of sense, right? So if you've ever tried to bond together wood that has been burnished, right, has that burnt characteristic to it, the joints aren't very strong at all. And that's because that burnishing actually burns off the hydroxyl groups and you're left with a carbon char. If you've ever tried to bond laser cut joint edges, right, laser cut wood edges, they don't bond. You get hardly any strength at all. And the other one that, again, I will also say is tropical wood that's very oily, such as like ipe. You try and bond those together. There's so much oil, you can't get to the cellulose. But if you look under the microscope, there's lots of pores. So if you have this in your head that it bonds through the pores of the wood, kind of get that out of your head because that is going to, how'd you say, push you in the wrong direction. Okay, then the other thing that you could get is glues of a different color. So I'm going to do this. Can you guys see that picture?
Mm-hmm. Yes.
So in some cases, your glue lines will turn black. So that black is caused because of the vinyl acid, the acetate group. So any PVA will eventually hydrolyze and produce acetic acid. The acetate group comes off and it forms an acid group, acetic acid, which is what is active in vinegar. And everybody's heard of or has done making a dye out of steel wool and vinegar, right? You get this black dye. Well, this is what's occurring in there. So if you get a black glue line, there's iron in your system somewhere. Now, where it comes from, I don't know. I do know that certain oaks will tend to pick up iron out of soil, especially if there's a old car buried somewhere around there or has been, rusted into the soil. We don't see it very much with other woods. I have heard of red. If you ever get a different color other than black, because we already know what black is. If you get another color, please send that joint in. We really want to look at it. I've heard of red joints on cherry. I've heard of green joints on some wood. If you ever get a different color, please send that in. We'd love to analyze it to figure out what's going on. All right, questions at this point?
Does this coloring in the joint occur more in the pore area?
I'm having a little trouble hearing you.
Does this happen more often in when you have end grain to end grain stick glue up?
Yeah, so end grain to end grain, they're going to be weak, right? I mean, that's just the nature of the fact that it's like gluing the ends of straws together. There's not a lot of cellulose to bond to. And the other thing that can happen when you're doing end grain to end grain is that the glue itself can, how'd you say, get pushed down the straws, and you can end up with a starved glue joint.
Okay.
So the best way to glue that, the quick and thick is very good because it's too thick to go down the straws, and so you get a good bond on end grain. But actually the best way is to take any wood glue, and any wood glue will work. You have to push it in. So take your finger and rub the glue down into the end grain to, how'd you say,
So the
it
pores,
basically plugs the pores of the wood so that then when you put some more glue on there and put it together, then it'll bond. But you have to satisfy those pores, the end grain. Otherwise, it's going to suck all the glue out of the joint, and then you're going to end up with a starved glue joint.
So I
but
got a
I,
question
that,
related to that. If you do that, do you let it dry?
No, you want to leave the glue as wet as possible when you put your bonds together. And we're going to go through why that is. And a little bit because we've gone through the cellulose is you want the glue to get as close as it can to the cellulose. If it gets to the putty point, right, where the glue can't flow, then it's not going to be able to get really close to and get to as many of the hydroxyl groups as it can. So
So glue.
always, and I've heard people go, no, I let it dry, and yeah, you can, but you're always going to get a weaker bond if it surface dries because that glue can't flow. And I've got some slides on that we're going to be going through.
Okay, I have a different question. You're saying that the glue adheres to the cellulose. You said that wood has 40 to 50% cellulose. So my question then is, what is the other 50 to 60%, and what effect does that have on gluing? What is the rest of that? You've already said it's not water.
Yeah, so that would be lignin. So lignin is the other portion that tends to be a little waxier. And that's how a tree actually works. The cellulose goes on the inside of those uh, pores, so to speak, and then the lignin kind of glues those kind of straws together. And that's what makes. And because it's a little waxy, the water as it hits that cellulose can get sucked up through the cellulose all the way up to the top of the tree. So there's kind of a continual path of cellulose that the water can feed through that goes up through the roots and into the leaves of the tree. And again, that's part of the wood science or the wood university presentation that I give.
So does the lignin enhance or decrease the gluability of the wood?
You can get some bonding to it, but it's not very strong. There's not a lot of hydroxyl groups to bond to. There are some, but there's not many.
All right,
And it has to do with how water wicks up through those pores in wood. It can't. If it was attracted to moisture, then the tree would not be able to wick water all the way up 300 feet into the air. So it causes the water to shoot up through the cellulose. Kind of like how paper towels, you stick a paper towel and just touch it into the water. Eventually, that whole paper towel will be wet because the cellulose just sucks water up. But the tree needs to also do it in segments, and so it's got to glue those fibers together in a way. Okay. Now everybody can see what do you guys see right now?
Wood glue applications.
Okay. So we're going to go through a little bit of the actual gluing now, the gluing process. And so when we do edge grain to edge grain or face grain to face grain, we have a ton of cellulose, right? And so that's why those joints are just so strong. There's so many hydroxyl groups to bond to in these things that really you're going to get the glue line is going to be stronger than the wood itself. As long as your wood is under, most of the domestic hardwoods here are going to break somewhere around 2,000 to 3,500 psi, and all of our glues are going to be stronger than that. As a matter of fact, we're having trouble finding wood that's strong enough because the reason is if I get wood failure, I'm not testing the strength of the glue. I'm just testing the strength of the wood. And so I'm really not getting an idea how strong our bond is to the wood because the wood breaks. So we use rock maple, and some of the rock maple will break in the 5,000 psi range. Some of this really slow growing maple out there. But it's getting harder and harder to find it. As a matter of fact, most of what we're seeing now of the maple just breaks around 25 to 3,500 psi. So we're really not measuring the strength of the glue itself. And I mean, so we have to pick and choose the wood to find the dense wood. Now the question comes in is, okay, so I've got to clamp my pieces together. So when we look at clamping, we need to look at the point where the clamp actually touches the wood. You get what's called a cone of force that goes out from that clamp face. And then it spreads out at about 45 degrees in each direction. Now, obviously, the stiffer the wood, the wider that angle is, the softer the wood, the less or the steeper the angle, so to speak. And so you want to put your clamping is to be designed to make sure that those pressures overlap. And there's an easy example I could show you where where you take a veneer and you try to use clamps to get that down. Now, in a lot of cases, you're not going to overlap on that, and in those areas, your veneer is going to warp, right? And everybody can kind of see that. So what you do in that particular case, if you can't get enough clamps on there to, get enough clamping pressure, you use either a caul or a vacuum bag, right? A vacuum bag will put pressure on the total surface area, right? So a vacuum bag is going to give you about 14 psi maximum, right? Because that's basically air pressure for a vacuum. So what is the clamping pressure that is necessary to glue stuff together? Well, a gentleman, so we typically on our tech data sheets, we say for softwoods, use 100 psi clamping pressure, the face pressure. For medium density like maple, use 150, and then for high density woods, use 200. Well, a gentleman called one time, he was using Jatoba, which is Brazilian rosewood, which is one of the harder woods available on Earth. And he was an engineer, so he had all of the clamping stuff down. Using the pressure we indicated, I asked him, did he wipe it with acetone to get rid of any oils to allow for better adhesion to the cellulose? And he was like, yes, I did all of that. So we asked him, we said, well, could you send us some in so we can do some testing? And most of the time, people don't send us stuff in, so we can't do the testing. But this guy did. And so what we did was we ran testing on 3 different species of wood. We ran poplar for softwood. Then we ran maple for the medium density, and then we ran his Jatoba for the high density wood. And then we used 3 different clamping pressures. And so we used a 5-pound weight was our low pressure clamping. And that worked out to be 0.6 pounds per square inch of clamping force. Then we used our regular clamping force, which we recommend. And then we used up to 1,000, we used 1,000 psi. And the reason we used 1,000 psi was there was a paper put out in 1998. I think it was 1998. PhD woodworker guy from wood laboratories, and he said that you could clamp all the way up to 1,000 psi without losing any strength. So we did that, and what we found was in every single case, the 0.6 psi gave us the strongest bond. Now, on the softwood, going from the 0.6 to the 1,000 psi, we really only lost about 10,000 or 10% of the strength. As we went to the maple, going from the 0.6 psi to the 1,000 psi, we lost about 25 to 30% of the strength. When we went with the Jatoba, going from the 0.6 psi to the 1,000, we lost, in some cases, 100% of the strength. As soon as it came out of the carver press, the joints just fell apart. And so we couldn't test them. And so we've kind of changed our recommendations for clamping pressure now. It's too long of a statement to actually put on our bottle because the bottles are already eye charts to try and read. But our statement on clamping now is use the least amount of pressure that it takes to get your pieces into the position you want them to be in when the glue dries. I know it's a little complicated, but there's a lot of stuff in that, right? And so you want to make sure that if your wood is warpy or doesn't fit really well, you're going to end up having to put a little bit more stress on it, right? But just note that if it's a softer wood, you're not going to lose much strength no matter how high you go. You'll crush the wood well before that makes an issue. But the harder the wood that you use, I mean, if you're using some of these tropicals that are pretty dense, you do not want to clamp them very hard at all because you can lose a lot of strength. In most of the cases, even going with our recommended clamping force, we lost 25 to 50% of that strength on the Jatoba. And so again, we've changed our recommendations for clamping because of that. Now, we still have on our website, if you note, it'll still say 100, 150 to 200. And the reason we left that on, twofold, because the old guys who, and not to say that we're not old guys, but the more traditional guys are like, oh, we've always had that on. We've never had problems. We're not taking it off. The other one is that if you're trying to force a bond together that isn't quite there, you got some warpage in your wood, you're going to need that amount of clamping pressure to get the soft woods and the medium density woods into shape to get it. But it comes down to, and everybody can kind of go, kind of slap your forehead and the light bulb goes off, is the better your joinery, the less clamping pressure you need, and the stronger the bonds are anyway.
Is that why joints work so well?
That if your joinery is good, that the boards fit really nicely together, you don't have to clamp them much at all, if any. In a lot of cases, especially in the poorer countries in Africa, they can't afford a lot of clamps. And as a matter of fact, most of them don't have clamps. They will do rub joints. Basically, you take the glue, put it on, rub the joint until you feel it kind of catch, and then they just set it off to the side. They make for very strong bonds, and we've tested that.
That's starving the joint, right? That would do.
Say that again?
It's like not starving the joint, the glue joint.
Right. So we're going to go next to what happens when you dry adhesive. So everybody's got this picture open in total assembly time?
Yep.
Okay. So this is actually what Titebond Original looks like under a microscope. They're just little microscopic balls of plastic that float in water. That darker color on the outside is the polyvinyl alcohol, and that's actually what sticks to the wood. And so as the glue dries, basically these particles just get closer and closer and closer together until they touch. And again, we've rubbed glue between our fingers, right? It's very slippery. And then all of a sudden it gets to that, what I call the putty point. If you took that glue that has puttied up in your fingers, put it on a scrap piece of wood, bonded it together, clamped it, and then broke it the next day, it would just come apart easily. And the reason for that is because those particles can't flow well enough to get to the cellulose, the hydroxyl groups that are on the surface. So we have the hydroxyl groups in the glue. We have hydroxyl glue groups on the cellulose. The water in there will help the hydroxyl groups kind of get together, but the particles have to be able to flow to get onto that surface. And so theoretically, if the particles are all the same size, I can still fill a jar 33% with water. So that putty point where the particles start to touch is about 67% solids. So on normal wood glues, which are 50% solids, normally I've got about 17 to 20% water to play with. With the quick and thick and the speed set, which are at 60% solids, I only have 7%. And so that's why they set faster, right? So what we do typically, we can play with how fast that putties up, right? We can play with the chemistry of the glue to give you different open and working time. So when we talk about open time, the open time is where the water is evaporating from the surface of the glue and the wood is wicking the moisture out of the glue. And everybody's finger glued, right? You put glue on there and your finger gets draggy right away, right? Well, when that glue feels draggy, that means that the wood has pulled the moisture out. You have a glue line that is already puttied up on the surface. And so you have to put a little more glue on to get it to be liquid and flow, right? Or if I just got to the putty point and put the two surfaces together, I wouldn't be able to move them. That would set immediately as soon as they touched, and then they probably would not even be in the right position. So then I am going to have to move the piece to get it into position. If I move it after the putty point, what's going to happen is I am going to tear the particles apart and they will not be able to flow back together again. If they don't flow back together again, I have now left a line in there of air. Right? That air will be a weak spot in the joint where stress will concentrate and it'll crack along that line. And it'll crack at a much lower strength than you were anticipating. And it's going to be lower based on how far past the putty point that you have gotten. Okay, so two things are, so that wood quickly is going to pull the moisture out. So then what you got is you want to put the glue on, then get your pieces together. Then you have what's called the total assembly time, which is to get it finalized in the clamp so there is no further movement. And when I say no further movement, I mean it only has to move half of a particle for it to break. And those particles are about one micron, which is 1/1,000,000th of a meter. So it's not a lot of movement. And there's nobody who can put stuff into clamps without it moving more than that. So you've got to get it in there while the glue is still in a liquid state, or your joint is going to be weaker. And it's going to be weaker in proportion to how far past that putty point that you have got. So the question comes up is, okay, one-sided gluing or two-sided gluing, which is best, right? So the answer to that is that everybody's correct. But there's advantages and disadvantages to either way that you're going to do it, right? So if you want thin glue lines, you have to be a single-sided gluer. And the reason for that is, if I'm a two-sided gluer, I am creating two glue lines that I am then going to put together. So my glue lines are always going to be twice as thick as a one-sided gluer, right? So if you want those invisible glue lines, you have to only put glue on one side and then get your pieces together. The problem with being a one-sided gluer is you're going to have a lot shorter time to get your pieces together. And I mean a lot shorter. And you're going to want to set an egg timer because it is going to, how do you say, challenge you to get enough pieces together. If you're using Titebond Original or Titebond 2, which are fast-setting glues, you may get one or two, maybe three pieces together before that glue is starting to set. Titebond 3 is going to give you twice as much time, so you're going to get more of them together. But again, if you've got a long segmented piece that you're putting together, it's going to be pretty difficult to get many of those together before that glue on the first one really is starting to set. So you got to keep that in mind. If you're a two-sided gluer, that's fine. You're going to get more time. You're going to use twice as much glue, which we thank you for. But you're going to get a lot more squeeze out, right? And it's going to be messier. So you're going to have to determine what's going to work for you in your specific application. Questions on that at this point?
You've just answered one of my questions already. That's a perfect explanation. Thank you so much for that.
Yeah. And then, so again, when we look at this, which is the working time, and then we look at clamping, which actually takes time also, right? Again, because you cannot clamp without the parts moving. My statement to you is you've got to incorporate all of that into your time. Now, if you want to, you don't really need to clamp if your parts fit together very well. And I'll restate that. You do not need to clamp if your parts fit together. If you can assemble them by rubbing them together and then move on to the next one, and they're all good, and you're no longer going to move any of those joints again, you're fine. You're fine. You don't need to clamp. And I know a lot of the segmenters, they use rubber bands, they use band clamps and all of that. You really don't need to. And again, just play with it. I'm not here to change how you do things. If what you're doing works for you, have at it. I'm not here to change anything. What I'm trying to tell you is these are things to look out for. If you're running into problems, these are the things that you may be seeing. Is that if I go past that working time, why are my joints, I drop a ring on the floor and it just seems to come apart. It shouldn't do that if the glue is very strong, but it could be that the glue had kind of set before you had it done, right? Because the wood should be breaking, unless of course you've got end grain to end grain, right? And in that case, will it break along the glue lines? Yes and no. If you get a microscope and really look at it, you actually see a lot of wood fiber. Those end grain, the ends of those straws are pretty brittle, and they tend to break at a relatively low strength. And so if you really look at it, you'll see it almost looks like a honeycomb structure with a bunch of fibers sticking out of it. So the glue actually does break the wood on an end grain to end grain bond. It's just that there's just so little wood to bond to. And so it go ahead.
When you're using saw blades, and say you're using a 100 tooth blade versus a 60 tooth blade, is that going to make a difference in the glue up?
So in cases, the rougher the edge, when you glue that up, if you break that, you're going to get very good wood failure, and it's going to look like the glue did a wonderful job. But if you actually looked at the strength that it broke at, because you got a lot of wood failure, you'll find that it breaks a little bit less strength. And the reason for that is because you're gluing to damaged fibers. It's kind of like people who sand with 80 grit before they glue up. They say because you want to rough up the wood. Well, the problem with that is that rough wood is damaged fibers. And if you glue to damaged fibers, it's kind of like, you see that little whisker of wood off of that edge. And then so you go, I'm just going to pull that off. And when you pull it, it just goes bam right down into the grain. And now you've pulled a big chunk of wood out. It's a similar phenomenon that happens in there is that, yeah, you're glued to those fibers. As soon as you start pulling on those fibers, they kind of break into the grain. And so they tend to break at a lower strength in most cases. Usually we recommend a nice sharp hand plane, 220 to 320 grit sand. You don't want to burnish, right? So can you use a belt sander? Yeah, but turn the speed down. You don't want to build up so much heat that you start burnishing that wood. And the burnishing doesn't even have to be blackened, right? Or even browned. It's just that glazy look to it. That glaze, because again, we're not diving deep into the wood to get a bond. It's just a surface phenomenon for the hydroxyl groups that are on the surface. And that's where we're getting our bonding. And so we want to make sure that the wood that we're bonding to is very strong, and that there's enough hydroxyl groups to bond to. Does that make sense?
So a 100 tooth blade is not good enough. You need to actually use the plane.
I mean, again, it will bond. I mean, I've made lots of furniture and stuff off of my, I think it's 120 tooth blade that I have, and I've had very, very strong bonds. Again, stronger than the wood. That's all it has to be, right? I mean, that's all it has to be is stronger than the wood itself, because that's going to be the weakest link in the chain. And so again, we want to be cognizant of what is the glue doing versus what is the wood doing. But again, I'm not here to change what you do. What I'm here is to just explain how the glue works so that you can make better decisions. Does that make sense?
Thank you.
Is there an ideal amount of glue to use? Or can you use too much?
So if your glue lines get thicker than 5 sheets of paper, then the strength starts to go down, but it's not by a huge amount. That those thicker glue lines will take longer to dry. Again, there's just more water that has to flash off or move through the plastic for the plastic to, how you say, all those particles need to melt together. So
Um, what about thinning the glues with water, or maybe you'll say something else. Particularly, I've heard guys say applying veneers to make it flow, to make it go thinner, to thin it a little bit and put it on. Any comments on that?
you can always thin it with up to 5% water without hurting the strength of the bond. Then every 5% after that will start to weaken the bond between 10 to 20%. But it will make it really, really thin. At some point, it gets so thin that you're not putting enough glue on and you end up with starved glue joints. So the viscosities that we come up with are such that when you squeeze the glue together, that it's got enough viscosity that it's not going to squeeze all of it out and starve the glue joint. So there has to be some viscosity to it. But if you're not putting a ton of pressure on it, then doesn't matter. It can be pretty thin. But then it starts to run all over the place, and that can be a problem also.
What's your thoughts on in some wood turning instances when you turn something and then you cut it apart and you plan to reassemble it? There's been I've understood that people recommend sizing the joint with a 50% reduced thinned glue, i.e. you thin the glue by 50%, size the joint, i.e. wipe a thin layer on there, let it dry, and then glue it up. And that seems to contradict what you've been just suggesting. So what could you just clarify for me?
I will tell you that will produce a weaker joint than if you just push the glue into the end grain. And we've tested this. This is the strongest end grain joint that you can get. And we tested the sizing the joint, letting it dry, then putting more glue on. The strongest joint is where you put the glue on wet, push it into the end grain on both sides, then put another line of glue there, and then put them together and then clamp. And you don't want to over clamp. Again, those straws can suck all of the glue out of the end grain. And pushing that glue in kind of gets you a hydro lock on the glue, so on those straws, so that they won't suck up any more of the glue out of the glue line. So you end up with a stronger bond doing that. But yeah, usually what we tested, it's usually between 15 and 25% weaker if you let it dry.
Bob, on a previous slide near the bottom, you talked about moistening the substrate to give you a little more working time. If you moisten the substrate with water, it's gonna raise the grain some, and you apply the glue and whatnot. How does that affect the glue joint overall?
So it doesn't hurt the glue joint actually, once you get you don't have to put a lot of water on the wood. I mean, you just have to get it above the 17% moisture content where the wood won't want to absorb any more water, right? So it's not a wet cloth. You want to just use a moist cloth. And then if you humidify the air around your glue up area, you can get an unlimited amount of working time. But just note that wood now is 17% moisture content. It's got to dry before the glue dries. Right? So it's going to take a lot longer for that joint to dry than, say, if you did not moisten the joint. And so in a lot of cases, you're going to have to multiply by 10 the typical times that you normally had it sit. So that's the drawback, that yeah, you can get an unlimited amount of time, but there's a lot more water that you got to get out of that joint. And we talked about sunken glue joints. We talked about, the glue has to dry to build strength, and already the ASTM test method for testing the shear strength of wood allows you a week to dry. So all of our testing is after a week of drying. Most people want to get moving on within a couple hours, or When I've actually seen on segments, people put together their segments with the quick and thick, and I've seen them start turning after 3 minutes. Now, my lawyer would tell me not to tell you that to try that at all. That 15 minutes should be good, but I mean, I've seen people start turning after 3 minutes, and then they don't no problems. But again, my lawyer's going to tell me officially it's 15 minutes. Now, if you're using Titebond 2 or Titebond Original, that's going to be about 30 minutes. Again, there's just the more water that you have, the glue is going to have to, that glue has to dry for it to build strength. And so the more moisture in that joint, the longer it's going to take. Now I can go through some of this if you guys want to, since this is really kind of turning. I'm not going to go through, motors and tenon joints tends to be the toughest to bond. Dovetails are mechanically locking, so you don't need a lot of glue on there. Most people will put glue on every surface. You don't need to if it's a mechanical locking. So what I'm trying to say is look at what you're trying to glue together. Understand the strength that piece is going to need. Like let's say if I'm making a vase, right? A segmented wood vase. How much stress is that going to see long term? Right? Probably not a whole bunch of stress. I mean, pretty much gravity is going to be the most stress that it sees. The most of the stress is going to be during the turning and the manufacturing of the piece, correct? And so we want to make sure that strength is there so that at those high speeds, it's not falling apart on you and exploding, right? Thinner it is, the drier that you want it, right? I mean, if the glue is still wet in the middle and I'm taking off the outside of both the inside and the outside, I'm going to get to a point where I'm at the wettest part of the glue, which is going to then be the weakest, right? So we just want to be cognizant of what's going on with the glue as it's drying, how that fits into the processes that we're putting our pieces through, and that those pieces are able to withstand the stresses, with the glue, the wood, and all of that. It just has to withstand the stresses that are going to be placed upon that joint. As long as, you got the right joints and the glue is dried, it's going to be fine, right? The problem comes in is, okay, I've moistened the joints. Well, if I've got a half-inch piece of wood, I've just put a bunch of water in the middle of that. How long is that going to take to air dry? So that might take a while, right? Because now I'm turning the outside and now I'm turning the inside. I'm getting to the middle of that wood pretty quickly, right? And now the outside, which is going to dry very fast, is going to look pretty dry. But what's the middle going to look like? Again, we just be cognizant of what the glue is doing and that. Now, somebody had some about veneering. I usually don't go into that. Most people don't do the veneering portion of that. If you don't have a press or a vacuum bag or anything like that, my recommendation is use an iron-on technique. Basically, you take an iron-on cotton setting, put glue on both sides, let it dry, and then iron it together. You want to make sure that you get uniform moisture between the substrate and the veneer. In a lot of cases, if the substrate is dry, which particle board, MDF, and you put a veneer on there, which is relatively high in moisture, that substrate, MDF, tends to be relatively dry. As it picks up moisture, it's going to expand a little bit. And then the veneer is going to shrink a little bit. And that's where you get a lot of the cracking that occurs is because of the moisture differences between the base and the veneer. End grain gluing we talked enough about. This is actually our no run, no drip is now called our quick and thick. It was our old molding and trim glue, but it can be used for a lot more than just molding and trim. So we remarketed the product and now it's selling very well. All right, so freezing. This is probably going to be important for you guys in Canada because we start getting calls about issues actually starting in October. So we want to keep the glues from freezing. And the reason we want to keep them from freezing, even though Titebond Original 2 and 3 will pass the freeze-thaw cycle, if it freezes once, probably still okay. The higher solids ones, like the Quick and Thick and the Speed Set, if they freeze once, they make good paperweights. But what happens is when the glue freezes, those latex particles are just floating around, happy as clams, but then the ice crystals start to form. Ice crystals and polymer particles don't mix well socially, and so the ice crystals tend to push them out of the ice crystals. Well, the issue is those glue particles are sticky. That's what makes them glue. And so when they get pushed together, they like to stick together. And so when you thaw it out, you've got to break those particles back up. So you may end up getting some gel particles in there. In some cases, like with the Quick and Thick, there's so little water in there that those particles get pushed together really, really tightly, and they aren't coming apart. And so you got to just make sure I recommend don't freeze them. If you've got an unheated shop, just get a box that you have a light bulb in. Just make a box, just keep them a little bit warm. If you're trying to glue stuff at cold temperatures, there is a chalk point on every bottle, right? And that chalk point is going to be the temperature at which, if you use it below, the particles will no longer melt together. So this is actually the formula for Titebond Original. I guess you've got it now on tape, so you don't need to write it down. But actually what happens is those particles will then coalesce into those, they'll start to touch, and then they need to coalesce into a film, right? And so this coalesced film, you can see this is a larger particle. This is one of the smaller particles. These are the real small particles. And basically to form a strong film, they have to melt together like that. If you go below the temperature at which they will melt together, they will what is called chalk. And basically they won't melt together. And to get them to melt together later, once it is chalked, you would have to get it up to 200 to 300 degrees Fahrenheit for them to melt together at that point in time. So probably a good thing. What will happen is the glue will turn kind of a whitish looking color. And in some cases, if it gets bad enough, it'll be actually dusty. I mean, the bonds will come apart and the glue will feel dusty. And the dustiness is just the plastic particles that you're rubbing between your fingers. Now, if you've got a shop that's cold, or you keep your wood outside, make sure you bring your wood in because the glue will quickly get to the temperature of the wood. So get it up to above that chalk point. Read the back of the bottle. That chalk point is on the back of every bottle. Titebond 3 has got like 45. That's going to be probably the lowest one that you can find. I believe Titebond Original Extend will go down to 40. It's not water resistant. The Quick and Thick, I think, is 50 degrees. So if you've got a shop that's not heated, you can get a couple of heated blankets from the Goodwill store and, just some cheap heated blankets. Just wrap your wood in that overnight and then glue up and then just drape the blankets over the wood to get it to dry. But the glue has to dry above that temperature. Once the glue has fully melted together, it doesn't matter. Then you can go down to minus 75, to the point where there's not enough oxygen in the air to breathe because the coldness has taken all of it out of the air. So it doesn't matter once the glue is dry. We want to look at sunken glue joints, make sure your humidity and moisture is controlled. Again, clamping time is going to vary, and it's going to vary depending on what the moisture content of the wood is, what your environmental conditions are. Again, with Titebond, some of the faster setting glues, I've seen people not even clamp those. Rub joints are very much worked with those fast setting glues. Once you get to Titebond 2 in that, I mean, we recommend 30 minutes on that. Again, I've seen people working with them, taking them out of clamps after about 5 to 7 minutes in a lot of cases. The glue is going to be after about 15 minutes, you're going to already be about 20% of the strength of the glue in most cases. So, and if you're looking at, say, Titebond 2 or 3, which is around 4,000, I mean, 20% is already 800 PSI. That's going to be stronger than a lot of the poplar that you're going to purchase. So again, you'll probably start getting wood failure after 20 minutes on some of the softer woods. So. Clamping pressure, we talked about that. Joint preparation, again, you want to make sure that you have strong wood with good hydroxyl groups to bond to. That's what my glue needs. And whatever you can do to get me more hydroxyl groups. And that's why when you look at joinery, all of that joinery is to get more face glue or side grain to side grain bonding, right? I mean, that's all of that end grain to side grain, all that joinery is to increase the amount of cellulose that can come into contact. Design your joints to handle the stress. Cleanup. Most of the water-based wood glues, really you just need some water around. Keep the glue wet if it gets on your clothes. And then all you have to do is just keep it wet and then just kind of running water, the particles just have to wash out, right? So just a little bit of mechanical work should get those particles moving off of the fabric. If you've gotten to the point where it has dried on the fabric, you can use a mixture of acetone water and vinegar. Acetone water and vinegar works together very well to soften any water-based wood glue, whether it be wood glue, whether it be construction adhesives, any water-based system will tend to soften with acetone water vinegar. Usually 1 to 1 to 1 works best. So if say you got Titebond 3, which is very water resistant, you put it on, it's going to soften the top layer, you scratch that off, and then you repeat as necessary to get it out. If your glue goes through a dryer cycle, you've actually melted all of those particles into a solid piece of plastic instead of, where you can kind of see the particles in most cases, then you basically just wear your glue proudly. So now we come to the 5 steps of successful gluing. Do a dry fit. Make sure that your joints just come together properly, right? And make sure they're all aligned. In that case, you can put masking tape on the joints if you want to do a roll-up joint. You can put tape around the outside, cut the end, unroll it, put the glue in, then roll it back up, right? So there's a lot of different ways that you can do that. But doing a dry fit will kind of help you make sure that, A, they're going to fit well. Because once you put the glue on, that's not the time to go, oh gosh, they don't fit all that well. And just remember, when you're putting glue onto those wood joints, that wood is going to expand. And so that may change things a little bit too. So you want to be cognizant of, well, now that I put the glue on, what's going to happen? And if you're unsure, make some test pieces and see what it's going to do. But again, the other thing is your parts should be within 1% moisture content. Otherwise, you're going to find that your joints are going to get stepped in some way. Okay? You want to prepare your glue, make sure it's in good condition. So when we talk about shelf life, so most of our glues have a 2-year official shelf life. But with good storage conditions, they tend to last a lot longer. So Titebond 2 and 3, which are reactive, if you store them at room temperature, usually you get 4 to 5 years of usable life. If you need longer usable life out of that, say you're buying gallons or 5 gallons because it's cheaper and you're just pouring it into other stuff, refrigerate it. A refrigerated Titebond 2 and 3 will last 10 years or longer. If you're using Titebond Original or those that are not water resistant, typically even at room temperature, they're going to last you about 10 years. But you always want to make sure you mix them before use, especially if they've been sitting around a little while. Because the larger particles are heavier, and so they're going to sink to the bottom. The smaller particles are going to go to the surface. When we test the glue, we mix it. So all of our testing is based on a certain particle size mixture. If you don't mix them, you're going to get smaller particles that come out on top. You're going to get large particles or mud that come out on the bottom. They're going to react a little bit differently in terms of how they're going to stack together. So you're going to get a different working time without a, how do you say, a mix. So just make sure that they're clean. You want to mask any iron stuff. Remember the acetate groups in the PVAs are going to cause black stains, and that black stain is in the water, and that water can dive very deeply into wood, so it can be very difficult to remove. Let's see. Prepare your cleanup items, get water handy. If you're using, say, a different type of glue, an epoxy, or a polyurethane glue or a CA glue, usually acetone will work pretty good on cleaning those up. But for water-based, water's much easier. Spread plastic, keep the stuff from. I actually watched a guy. He was doing his glue up for his ring on a segmented, and he didn't have anything down on the table. He glued his thing right to the table. We had fun trying to get that off without breaking his ring. So just make sure you protect against drips or glue that goes in places you don't want it to go. Then you do your glue up, right? You want to make sure that your wood, the substrate, is above the chalk point. The glue's quickly going to get to that temperature. Consider gluing in stages, because if they're open in assembly time, you've got too many pieces to put together. You may be needing to put fewer pieces together, let them sit, and then you can start adding to them at a later time. Wipe joints with acetone, especially for oily tropical woods. It will always strengthen the bond if you wipe any wood with acetone. Now, for most of the domestics, it's not going to be much, unless you're using cedar. Cedar, some of that cedar can get pretty oily too. So wiping with acetone will always get it. Make sure your glue is in good workable order before you start. Titebond 3 is notorious for getting gels in it if it's relatively older or hasn't been mixed for a while. And so you start gluing, and then a big gel will plug the cap, and now you're in the middle of trying to clean the cap out really during your glue up process. And so you want to make sure. Get a timer. Get an egg timer. Set that egg timer for the amount of time that you have, because once the glue hits the wood, it seems like the time-space continuum changes. Time either speeds up or slows way down, and you're left with parts that aren't quite in the position you want them to be in when the glue dries. So the other thing is, you got to wait for it to dry, and that's going to depend on what you've done. If you've added extra water, you're going to have to wait more time. Note that if you want a smooth surface, you got to wait for the glue to get to the moisture content that it's going to be in use. And if it's going to a drier climate, you're going to want to dry it out before using it, even to the point where if you've got a vase that's going to Arizona at some point in time, put it in your oven for a little while. Dry that wood out, and then do your final sand on that. So that's all I have at this point. Questions?
Will we have access to all these wonderful slides for quick access?
Yeah, I can send a presentation. Just send me an email asking for it, and I'll get it to you guys, and you can post it on your website. Again, this is educational for everybody. This is not like an advertisement for Titebond, obviously. This is one where we're trying to get everybody to understand how glue works, so that when you do use glue, you'll have a good experience. And if you don't have a good experience, you're not going to call me and tell me how bad my glue is. You're going to kind of sit back and go, well, what maybe happened here? And if you do call me, it's to find out, well, what else am I not thinking about? What else could have gone wrong? Because I can tell you, I've been working for this company for 15 years. We've never had a problem with the glue. It's never been a problem with the glue. Our quality systems are such that it can't happen. It's also the fact that it's not rocket science. We got the equipment. The equipment works. If the equipment works the same every day, you add the same amount of stuff into the equipment every day, you feed it in at the same rate, which is what our quality systems handle, you're always going to come out with a product which is consistent. And so 15 years, it's never been the glue. And if you call me and have a good conversation where you're not going to tell me that it's my problem and that you're not going to talk to me about how and what went together, then we can't help you. But if you're going to want to call and we'll talk about it. At some point I may not know, and I may ask for samples. And if you send the samples in, then we can find out. But it's difficult once it's already glued up to find out. We sometimes it takes a bit of digging to figure it out. But yeah, no, this presentation is for anybody you want to send it to. This is educational, and it helps everybody in the industry.
Well,
Well,
thanks
I
a
got
lot,
a
Bob.
question.
That'll be great. What we will do is, you've given me a copy of the presentation. I have it. What I'll do, we have our club meeting tomorrow night. I'll bring a copy of it and give it to our secretary to have it added to our website.
Okay, yeah, because I sent you a copy. Yeah, that's right.
Yeah, you bet.
Yeah, I got a question, and I've tried to find the answer to this on the internet, and I can't find it. I'm interested in the how long glue will last, and I do not mean shelf life. Once it's applied and the material is put together, how long is that glue effective before it evaporates, crystallizes, whatever, I don't know, starts to let loose?
Yeah, so the PVAs we do know they've been out really since the 1950s, and we have not seen any breakdown of the PVA polymer itself. Now, scientists at this point in time are working on changing the biology of certain bacteria to break down plastics. Now, if that ever occurs, then that may be an issue, right? If there's bacteria that can now eat plastic, this is the PVA is plastic, then it'll be a food source for them and it'll start to break down. But at this point, bacteria have not, how you say, found the right genetics to break down PVAs or any of the other synthetic polymers at this point.
Okay,
So-
that's helpful.
Yeah, so at this point, it's been since 55. So we know 75, 70 years that it'll last at least.
But heat can cause it to let loose, correct?
Heat can soften it. So the PVAs start to soften around 280 degrees
Okay.
Fahrenheit. Sorry. It's the United
Yeah.
States. We
Yeah,
haven't
yeah.
figured out how to use the metric system yet.
And this is a bit beyond what we're talking about here tonight, but contact cements. Now the old petroleum-based ones, guaranteed after about 10 years, they're going to let go because it evaporates.
No, it doesn't
But the
evaporate.
water-based ones, do
Yeah,
they
no,
let
no, no,
go as
no.
well?
So that's not the case. They don't evaporate. So what happens is ozone and oxygen will cause them to get brittle. And so they start to scission the bonds of the polyisoprene, which is what is the polymer for contact cements. And so over time, yes, they will give up. And usually, if you've got an arcing source, so let's say you got an outlet that has a little bit of a short to it, it's going to create ozone. And the ozone is what breaks that down very quickly. Oxygen a little bit slower, but ozone breaks it down very, very quickly. So if you've got an ozone source in your house, that contact cement may last a few years before it starts to get brittle. It's kind of like with rubber bands. It's the same thing. Rubber bands, you put it in a drawer over time, they get real brittle and they break. It's the same chemistry. It's the isoprene in there that does that.
Okay, thanks.
I have a question regarding your translucent glue.
Uh-huh. The Titebond
Uh,
translucent?
Pardon me?
Titebond translucent?
Yes. Does it have a really less visible glue line than your PVAs, your other
So
PVAs?
yeah, so PVAs when they dry, they're going to give you something that is what translucent is frosted, right? So it's like looking through a frosted piece of glass. The thinner that glass is, the better you're going to be able to see through it. The thicker it is, the more frosty it's going to look. So on thicker glue lines, they can look white. So basically, Titebond translucent is really our Titebond original without any dye added. So we add a little bit of dye to most of our wood glues to give it wood color. And the reason we do that is because for that very reason, white glues tend to have like a frosted look to it, especially on thicker glue lines. So if you color them, you can make them match the wood. So any of our wood glues, you can add up to 5% dye, pigment, or whatever you want to them. Turn them any color that you want. Now I've seen a segmenter guy, he takes all of his wood glues and puts a black dye in them. He uses trans tints, and he was starting to use some RIT dyes in there, and he does that double glue line. So he puts the glue on there, lets it dry a little bit, puts a little more glue on, gets those glue lines real thick, and puts it together, and it looks like he's got a black veneer between each sheet or each piece. So you can make your glue lines any color. You make them pink, purple, yellow, gray, orange. Just add dye to the glue, and you can go up to 5%. And 5% dye is a ton amount. Our Titebond original, I think we put in 0.05% dye in it, and it gives it kind of that yellowish look to it. And it tends to match maples and your lighter shades of wood better than, say, a white glue does. Well,
Water-based or acid-based or alcohol-based dyes?
Yes. So any of them will work because the PVA is pretty, how do you say, it's pretty resistant to bases and acids. So you can use either, if you're going to use a pigment though, if you're going to use a solid, powdery pigment, just add 50-50 pigment and water, and then just a drop of Dawn dish detergent. The dish detergent is going to help that powder wet out better, and so it'll spread more evenly throughout the adhesive itself. But yeah, give it a try. It's pretty cool. Some of the things that you can get, especially if you're segmenting, to do black glue lines. It really looks like you've put a black veneer in between each of the pieces.
And the particles in the dye don't affect the strength of the plastic film in between?
Up to 5%. Anything above 5%, it does. So, but 5% is really high. I mean, if you're going to put dye in, you want to be somewhere less than 1%. Otherwise, it's a lot of dye.
Well, you've got a pretty quiet audience
Lots
now,
of
so it
good
looks like you've
information.
answered most of our questions. Hopefully there's some more questions out there.
Okay, I
Well,
have one.
Yeah.
I have probably personally contributed to several Titebond trips with the amount of glue that I have used over the years, buying it in gallons and the amount of squeeze out that I get. So I've learned a lot here.
Well, thank you. We do appreciate that.
Yeah, hopefully it's helped. Anyways, just over the last couple of weeks, I've been making some charcuterie boards and using Titebond 3. Is that the one that you would recommend for making sort of like charcuterie boards and or cutting boards?
Yeah, so Titebond 3 will actually go through a boiling water soak, which Titebond 2 will not. Now, we would always recommend to use a water-resistant glue for any food items, right? Because somebody's going to wash them at some point in time.
Okay, and that said, when just your notion of not having to clamp, like everything I clamp, and of course the metal on the bar clamps touches the wood, and so then I get that black that you were just talking about, and then because I clean off most of the squeeze out, but then I let it dry for 24 hours, and then I have to run it through the sander and everything to get rid of all the the extra glue, etc. So I'm just wondering, could I amend my practices significantly and just start maybe like taking the first, say, 3 pieces of wood and doing a rub joint and just letting it sit and then keep adding to it, or what?
Yeah, you can do that. As a matter of fact, just as a matter of fact, I to prove my point that you can do this without clamping, I made a tabletop with plywood, basically, and just stacked them together into a table, and it is as strong could be. No clamping was used. Now, the problem is that as I stacked them, it got a little bit of a wave in it. And so again, the clamping is there to get your pieces into the position you want them to be in when the glue dries. Because now I can't do anything about the wave, so I just had to, I used a fill, an epoxy fill to then fill that to make it a level surface. And it looks really nice. Now with your cutting boards, one of the better ways of removing the squeeze out is to wait 20 minutes, 20 or 30 minutes, right? So when you wait that 20 to 30 minutes, the glue has puttied up, right? So once it putties up, it won't dive into the wood any longer. So it may look like as you're scraping, it's getting all over the place, but in essence, it's just rolling on the surface. It's not wetting the surface out. And so it tends to sand off very easily and the next day.
But I always have about 100 pounds worth of clamps on the whole thing. So after 20 minutes, are you suggesting then that I would either A, not go through that whole clamp exercise, or B, take the clamps off and clean the board up?
So you're probably okay with Titebond 3 taking it out of the clamps in an hour and a half or 2 hours in most cases. And the glue should be still relatively soft at that point in time. You should be able to take a sharp chisel and get most of it off.
Okay, that'll make a big difference.
So, but then before you put it through your sander and stuff, you want to let it dry overnight, at least 17 hours, if not 24. Again, if you sand it too soon, you may end up with the sunken glue joints, and you may be able to start to feel those ridges. So your final sand should really be that 3 days to a week, or 3 weeks if possible. Just leave them lay around to kind of fully dry out.
All right, thank you.
But again, that doesn't, doesn't do well for your production, right? In getting stuff through the shop.
Sure. Not in a rush. So.
But Titebond 3 is great because it can go through boiling water soak, and if anybody puts your charcuterie board or that into a dishwasher, I always tell people it's easier to refinish a cutting board than it is to fix a cutting board.
Sure. I always give them a handout and in big letters, make a note that it's not supposed to go through the dishwasher.
But it's going to eventually, yeah. How I always tell people is eventually it's going through the dishwasher because unfortunately, if the person passes away, somebody's going to put it in a garage sale. Somebody's going to buy it for $1 and they're going to go, it's $1. They'll put it through the dishwasher. Unfortunately. Well, I appreciate the time. If you guys have any questions, we do have an 800 number on the back of every bottle. You can ask for Bob. I train everybody in the lab, who answers the phones. They're pretty good at answering these questions too. We all go to Mark Adams Woodworking for training, so we've all done some woodworking. I've got my master's in woodworking. I'm working on my fellowship at this point in time, so hopefully we'll get that next year. So, okay.
I would like to thank you so much for providing all this information, Bob. It's been fantastic, and I'm sure I speak for everybody here. We're really, really happy that you took the time out of your busy schedule to join us here and educate us.
Okay, great. Appreciate it. Thanks, guys.
Thank you.
Thank you very much.
Thanks, everybody, for attending.
Thank you, everybody.
Bye, Bob.